Okay, in this video we're going to keep going looking at our continuing to higher steric numbers. So here we're going to start with a steric number of 5 and looking at the variations once we start adding lone pairs into these structures. So again, just as a quick reminder, this is our trigonal bipyramidal structure when we have a steric number of 5. And this is going to be the electron pair geometry for all of these structures that we're going to look at in this, this section of the video. So if we have no lone pairs, so this is our 0 lone pairs, then of course the molecular geometry and the electron pair geometry are the same. So this is like PCl5. Again, these are arranged where we have our 3 atoms here are our equatorial, because they're sort of along the equator of the molecule. I think I may have spelled that wrong. But and then our 2 up here and down here are the axial. Right, we have different bond angles here. There's a 90-degree bond angle here, whereas between the different chlorines here, there's a 120-degree bond angle. Okay, so now we can think about adding lone pairs. And unlike all the other ones, where we add the lone pair here matters. So there's 2 possibilities. So I'm just going to draw a central atom Q and use X's to represent our other atoms in the structure. So we could put our lone pair axial like this. And then have our other atoms all in the same spots, right? And so this is one possibility. And the other option is we could put the lone pair over here, and then put all the other atoms over here. And basically the question is whether the lone pair is axial in this structure, or whether it's equatorial. Maybe I did spell it right. You'll have to double check and see. Right, but it's equatorial. That's what's wrong. Okay, because it's equator. Anyway, so one of these is going to be favored over the other, and let's think about why. If we have an axial lone pair, so considering this one first, we need to think about, is this minimizing the repulsion? So lone pairs want to take up more space. This is what we've already talked about, that they're going to push on the other atoms more. And so we want to give lone pairs as much space as possible. In this structure, we have 3 atoms at 90 degrees. Of course, it won't be exactly 90 degrees when it pushes on them, but we have 3 90-degree angles here. They're all relatively close to this lone pair. And so it doesn't have as much space as it could if we look at this structure. We have the equatorial lone pair, where there's only 2 atoms at 90 degrees. And then 2 other atoms are going to be at 120 degrees, but that's a lot further away. And so what we get is that this side, where we have an equatorial lone pair, this is the only geometry that exists. This side over here with the axial lone pair, this never happens. There's just, the lone pair wants as much space as it can get, and it gets that by being in an equatorial position. So when we add lone pairs into this bipyramidal here, trigonal bipyramidal structure, because trigonal pyramidal is different, the lone pair will always favor the equatorial position. It's never going to go in the axial position. And that's going to be true even when we start adding more lone pairs. So that's going to be our guidance, is that we're always going to put lone pairs into the equatorial position and not the axial position. All right, so we're going to add it to the equatorial position. What does that leave for? All right, so we have this structure here. I'm just going to redraw it so we have clarity and it's not so cluttered like it is over there. Keep wanting to make these fluorines. We'll just make them X still. Okay, so what we're left with is this structure here. Again, we're going to, now this is still an electron pair geometry of trigonal bipyramidal, but if we ignore this lone pair, right, it's there, but I'm just going to erase it just so we can look at just the structure of the atoms. We get this structure here. And the name of this is called seesaw. Now, why is it called seesaw? Well, you can imagine turning this 90 degrees on its side. And so we'll have these x's pointed sideways. Again, our lone pair is up here. And we have now one x pointed backwards and one x pointed forwards. Oh, I made those h's. I keep wanting to put specific atoms in these. Right. And what you can imagine is this is going to look a little bit like a seesaw on the playground. This is where you have one person would sit over here, one person would sit over here, and this whole structure can rock back and forth. So it's going to be something like this. There's like a little fulcrum. It's going to go back and forth with two other bonds sticking out either side. Right. And so that's where this gets its name. It's a seesaw structure. All right. So you can imagine a couple little electrons playing back at seesaw on a molecule or something, if that helps you remember what this structure looks like. All right. Now let's look at the bond angles. Again, we're going to get our bond angles are still going to be based mostly on this trigonal bipyramidal structure. So this is going to be 90 degrees, but not exactly 90 degrees because, again, this lone pair exerts a lot of influence. And so the angle between these still axial x atoms and the equatorial ones is still going to be 90 degrees, but a little bit less than that. Same thing for this. This is going to be pretty close to 120 degrees, but maybe a little bit less than 120 degrees. Again, all the bonds are going to get smushed a little bit because of this lone pair. Okay, so that's one lone pair. Now, our second lone pair, like I said, is also going to get added into the equatorial position, not into an axial position. So lone pairs preferentially will always go in the equatorial position to give them as much space as possible. Right, so this, just to reiterate, this is one lone pair. Our second option, of course, is two lone pairs. And if both lone pairs go on the equatorial position, what does that leave us with? So we'll get a Q. We have our two axial x's here. And we'll put one x here and then our lone pairs over here. So again, our electron pair geometry is still trigonal bipyramidal, but now if we ignore these lone pairs and just look at the q's and the x's, what we get is this is called a T-shaped structure. And the name's pretty obvious here that this looks kind of like a T. So if you tilt it on its side in particular, you get something that looks like this. It looks roughly like a T, right? Our Q being here and our X's being here and here and here. All right, and so this is our two lone pair Sn equals 5 structure. So our molecular geometry is T-shaped if we have two lone pairs, but 5 electron pairs around, but 2 of them being lone pairs. Okay, so let's go ahead and continue. We can look at additionally 3 lone pairs. And still, our lone pair is going to add to the equatorial position, not the axial position. So we end up with our Q in the middle, our two axial x's here, and then our lone pairs are going to be all around in the middle here on the equatorial positions. And this is just another way to get a linear molecule. Again, if we ignore the lone pairs, this angle here, and this one will actually be exactly 180 degrees because the lone pairs are pushing on both of them the same amount. So we end up with a linear molecule. Again, with the T-shaped, these are 90 degrees, but are going to be a little bit less than 90 degrees. Okay, and then we could go 4 lone pairs, but that's also going to be linear because it'll just be 2 atoms bonded together. All right, so we'll do one more video, which will be for Sn equals 6, looking at the octahedral geometry and when we start adding lone pairs there.